So remember affine control loops, all of it. Here is the example. And basically what we have is, by doing this analysis, what we get is a system of recurrence equations. So you are computing all the points, for example, a variable x in some point, all the points in a domain. And in order to compute at x at some point z, you are going to read x at fz. This function f is my dependence function. And in the simple examples that we saw, this was always a translation. It was just z plus constant. Fz was z plus constant vector, right? But in the polyhedral model, it is more general. We are allowed more general dependencies, okay? So here is my definition of a recurrence equation, and the dependence function is some mapping from Zn to Zn, okay? All right. Now I'm going to extend this slightly, and I say that basically uniform equations are the ones where Z is some translation, and affine recurrence equations, which is basically all the class of polyhedral programs, are defined by affine recurrence equations, where the dependence itself, the function f, is some linear function of Z plus constant, okay? A system of equations is when you have multiple mutually dependent equations, okay? They could be uniform or affine. And in polyhedral equations, you can also have reductions, which I will talk about a little bit later, okay? So polyhedra are represented by sets of linear inequalities. You know that, okay? And there is either a vertex or the set of constraints, as I talked about briefly yesterday. Okay, so here is the mother of all transformations. We talked about this, yesterday, but I simply said, okay, you take a polyhedron and you map it somewhere. Okay, now I'm going to tell you how to take the program representation. So you have done the analysis and you have constructed these equations, okay? And they represent what exactly is being computed by the program, okay? So I have some variable u defined over its own domain, and it applies some function to two values. One is the u from some other point and v from some other point, okay? And similarly, I have a variable v which depends on u and v. So I have self-dependencies of u on itself. I have a cross-dependence of u on v. And for the equation of v, I have a self-dependence of v on itself and a dependence of v on u. And each of these is a different function. Fuu is one function, fuv is another function, etc. Okay. Okay. We are given this equation, and we are given a function t. This is that transformation that I was talking about. It takes a rectangle and makes it into a parallelogram. That is the mapping of original to new indices. And my job is to construct an equivalent program representation in the form of a system of recurrence equations. Okay, here is a pictorial view of what I want to do, and I'm just showing a small number of instances of dependencies. If you take a point A in the domain of U, it depends on some point B in the domain of U by applying the function FUU. This is a self-dependence of U on itself. That parallelogram on the left represents the domain of the variable U. The trapezoid on the right represents the domain of the variable V. Okay? And I am showing these four arrows. In general, if I take some other point over here and apply FUU to it, I'll get some other point here. May not be the same as B, may be different. The dependence functions don't have to be one-to-one. I can have a program in which ij depends on ii, for example. That means many points depend on that. Okay? So the dependence patterns, these affine functions can be it can be very rich. Okay? Then I have a transformation T. Here is this transformation that takes this parallelogram in red and transforms it in some way, but it has to be a bijection. Okay, so it maps A to A prime, B to B prime, C to C prime, and in general it gives me the image of that polyhedron by the function t. And if you remember yesterday, I gave you the simple rules to construct the image of this polyhedron by a transformation t, by looking at T inverse and working with the constraints of the polyhedron. Remember that simple rule? Wherever there is I, replace it by T, wherever there, or P, and wherever there is J, replace it by T, or the expression that, that is the inverse mapping. Okay, so you can construct this T of du. What is difficult is how do you construct these new functions? In the original program, I had a function that mapped A to FUV, to M. I had a function that mapped A to another function that mapped A to B. I had this function that mapped L to M and L to C. Okay, and now I have to construct these new functions. Okay, so how do I construct these new functions? The simplest function is FVV. In the original program, I had this red function that mapped L to M. In the new program, what is that function? Unchanged. Neither L nor M has moved by my transformation. I only applied the transformation to the domain of U. I did not touch the domain of V. So the old mapping that was function that was telling me how to go from L to M remains unchanged. What about the function FVU prime? I want to go from L to C prime, which is the image of C by the transformation T. Can I think of a simple rule by which I can go from L to C prime? Yes?
If we apply the same transformation to the function also, then
Yes, the thing is, my job is to mathematically construct this new function f prime vu given these old functions fvu, fuu, etc. Okay, and I want to do it systematically and correctly. So the rule is, in order to go from L to C prime, I apply a function that first goes from L to C, and to that point I apply the transformation T, because C prime is the image of C by the function, by the function T, right? So the rule to construct the new cross dependence of V on U is to first apply the old dependence function, and to that apply the transformation. All right. Now let's look at this function f prime uv. Okay. In the old program, I had a function fuv, which was a mapping from A to N. You're seeing that arrow? In my new program, A has moved to A prime. Now I have to construct a function that maps A prime to N. How do I do that? Using these functions, the old functions that I had in red. To A prime, I first apply T inverse. And to the result of that, I apply the old function. You see that? From A prime, if I apply T inverse, I go back to A. And to that point, if I apply the old dependence function, I'm getting to n. So this is the composition of those two functions, is the mapping from a prime to n. So now let's look at the fourth one, the mapping from a prime to b prime. How do I systematically construct the new self-dependence of u on itself in the new equivalent program? Hint, 3 steps.
So first we take the pre-image of A dash, then we
Yes.
apply the function, and then take the image of B.
To the point a prime, you first apply T inverse. To the result of that, you apply the old dependence function to get to B. To the result of that, you apply the T and you get to B prime. Okay, so this is in the pictorial view. In reality, this is how you construct the equations. You compose, this circle represents function composition, and function composition is right associative. That means when I see T circle FUU circle T prime, I mean I apply T prime first, then I apply FU, UU, then I apply T. So the composition of these 3 functions, remember these are linear functions represented by matrices, by 3 by 3 matrices basically, right? So that is what the compiler constructs in the polyhedron model. And now you get a new function, u of z depends on u of that new function applied to z. So that is my new dependence function. And similarly, this is simply the composition of fu, v, and t, t prime. I've written t prime, but what I mean is t inverse. Okay. And the self-dependence of v on itself has not changed. The cross-dependence of v on u has changed by where you first apply fvu and then you apply t. And you have changed the domain by t of du. So this system of equations preserves the semantics. Okay? So actually this is actually a good time to stop about about change of basis or program transformations, because you guys asked nice questions about change of base of transformations. So